Yes, the direct current link voltage requirements for an online double conversion uninterruptible power supply can vary depending on the uninterruptible power supply technology used. For ferro-resonant uninterruptible power supplies, they typically use a lower direct current link voltage, around 2.2 to 2.5 times the route mean square input line voltage. For 480 volts alternating current input, the direct current link voltage would be approximately 1056 to 1200 volts direct current. The lower voltage reduces the stress on the transformer and other components. For pulse width modulation uninterruptible power supplies, they use a higher direct current link voltage, usually around 3 to 3.5 times the route mean square input line voltage. For a 480 volts alternating current input, the direct current link voltage would be approximately 1440 to 1680 volts direct current. The higher voltage improves efficiency and reduces harmonic distortion. For step wave, which includes 6 or 12-step uninterruptible power supplies, they use a direct current link voltage that is typically close to the peak output voltage. For 120 volts alternating current output, the direct current link voltage would be approximately 170 volts direct current for 6-step, or 340 volts direct current for 12-step. The lower voltage simplifies the output transformer design. Let's summarize. For ferro-resonant uninterruptible power supplies, the direct current link voltage requirements are 2.2 to 2.5 times the route mean square input line voltage. For pulse width modulation uninterruptible power supplies, the direct current link voltage is 3 to 3.5 times the route mean square input line voltage. And for step wave either 6 or 12-step uninterruptible power supplies, the direct current link voltage is close to the peak output voltage. It's important to note that the actual direct current link voltage requirements may vary slightly depending on the specific design and manufacturer of the uninterruptible power supply. The differences in direct current link voltage requirements stem from the inherent operational characteristics of each uninterruptible power supply topology. The ferro-resonant uninterruptible power supply relies on a saturated transformer to provide voltage regulation and isolation. The low direct current link voltage is sufficient to drive the ferro-resonant transformer and achieve the desired output voltage. The use of a lower voltage reduces the stress on the transformer's insulation and other components, contributing to increased reliability and longevity. However, ferro-resonant uninterruptible power supplies tend to be less efficient and produce higher harmonic distortion compared to other technologies. Pulse width modulation uninterruptible power supplies utilize high-frequency switching of semiconductors to generate the desired output voltage waveform. The higher direct current link voltage provides a greater voltage headroom, allowing for more precise control over the pulse width modulation process. This results in improved efficiency, reduced harmonic distortion, and better dynamic response. However, the higher voltage also increases the stress on the switching components, requiring more robust designs. Step-wave uninterruptible power supplies, particularly the 6-step and 12-step variants, employ a multi-pulse transformer to synthesize the output voltage waveform. The direct current link voltage is typically close to the peak output voltage to simplify the transformer design and reduce the number of transformer windings. This approach offers a compromise between efficiency, harmonic distortion, and component stress. The choice of uninterruptible power supply technology and direct current link voltage depends on the specific application requirements. For applications where reliability and robustness are paramount, ferro-resonant uninterruptible power supplies may be suitable. For applications where efficiency and power quality are critical, pulse width modulation uninterruptible power supplies are often preferred. Step-wave uninterruptible power supplies can provide a cost-effective solution for applications with moderate performance requirements. In addition to the topology, several other factors can influence the direct current link voltage requirements of an online double conversion uninterruptible power supply. These factors include the input voltage range, the output voltage regulation requirements, the battery voltage, and the component ratings. The input voltage range specifies the allowable variation in the input alternating current voltage. The direct current link voltage must be high enough to ensure that the uninterruptible power supply can maintain the desired output voltage even when the input voltage is at its minimum value. The output voltage regulation requirements specify the allowable variation in the output alternating current voltage. The direct current link voltage must be stable and well regulated to ensure that the output voltage remains within the specified limit. The battery voltage determines the amount of energy that can be stored in the battery. The direct current link voltage must be compatible with the battery voltage to allow for seamless transfer between alternating current and battery power. The component ratings specify the maximum voltage and current that the components can withstand. The direct current link voltage must be within the component ratings to prevent damage or failure. When selecting an online double conversion uninterruptible power supply, it is important to consider the direct current link voltage requirements and ensure that they are appropriate for the application. Consulting with a qualified power systems engineer can help to ensure that the selected uninterruptible power supply meets the specific needs of the application. Understanding the relationship between the different uninterruptible power supply technologies and their direct current link voltage requirements is crucial for selecting the right uninterruptible power supply for a given application. This knowledge also aids in troubleshooting and maintaining uninterruptible power supplies effectively. Factors influencing direct current link voltage include input voltage variations. A wider input voltage range necessitates a higher direct current link voltage to maintain output voltage regulation during low input voltage conditions. Output voltage regulation requirements also play a role. Tighter regulation demands a more stable and precisely controlled direct current link voltage. Battery voltage is another factor. The direct current link voltage must be compatible with the battery voltage to ensure seamless transfer between alternating current and battery power during outages. Component ratings are crucial as the direct current link voltage must remain within the voltage ratings of the uninterruptible power supply components to prevent damage and ensure reliable operation. In summary, selecting the appropriate uninterruptible power supply technology involves careful consideration of the application's specific needs, including power quality requirements, budget constraints, and desired level of redundancy. Each type of uninterruptible power supply offers unique advantages and disadvantages, making it essential to weigh these factors before making a decision. Also note that the actual direct current link voltage levels can vary slightly depending on the design choices made by the uninterruptible power supply manufacturer. These design choices can be influenced by factors such as the specific components used, the desired efficiency, and the target cost. Therefore, it is always best to consult the manufacturer's specifications for the specific uninterruptible power supply model being considered. Furthermore, advancements in power electronics technology continue to drive innovation in uninterruptible power supply design. New topologies and control techniques are constantly being developed to improve efficiency, reduce size, and enhance reliability. As a result, the direct current link voltage requirements of uninterruptible power supplies may continue to evolve in the future. Keeping abreast of these advancements is essential for staying informed about the latest uninterruptible power supply technologies and their capabilities. The root mean square input line voltage is the effective value of the alternating current voltage. It is calculated as the square root of the mean of the square values of the voltage over one cycle. The peak output voltage is the maximum instantaneous value of the alternating current output voltage. For a sinusoidal waveform, the peak voltage is equal to the root mean square voltage multiplied by the square root of 2, which is approximately 1.414. Harmonic distortion refers to the presence of unwanted harmonics in the alternating current voltage or current waveform. Harmonics are sinusoidal waveforms with frequencies that are integer multiples of the fundamental frequency. High levels of harmonic distortion can cause problems such as overheating of equipment, interference with communication systems, and reduced power factor. Efficiency is a measure of how well the uninterruptible power supply converts input power to output power. It is defined as the ratio of output power to input power, expressed as a percentage. Higher efficiency means that less energy is wasted as heat. The direct current link voltage plays a crucial role in the overall performance of the uninterruptible power supply. By carefully selecting the appropriate direct current link voltage for the chosen topology, designers can optimize the uninterruptible power supply for efficiency, reliability, and power quality. Remember that the direct current link voltage is not the only factor that determines the performance of an uninterruptible power supply. Other factors, such as the quality of the components used, the effectiveness of the control system, and the thermal management design, also play important roles. Therefore, it is essential to consider all of these factors when selecting an uninterruptible power supply for a specific application. Also, regular maintenance and testing of the uninterruptible power supply are crucial for ensuring its continued reliable operation. This includes checking the battery voltage, inspecting the components for signs of wear or damage, and verifying the output voltage and frequency. By following a regular maintenance schedule, you can help to extend the life of your uninterruptible power supply and prevent unexpected failures. The specific maintenance requirements will vary depending on the uninterruptible power supply model, so it is important to consult the manufacturer's documentation for detailed instructions. It is also recommended to keep a log of all maintenance activities performed on the uninterruptible power supply. This log can be helpful for tracking trends and identifying potential problems before they become serious. Direct current link capacitors are a critical component in uninterruptible power supplies, responsible for smoothing the direct current voltage and providing a stable energy source for the inverter stage. The selection of appropriate capacitors is crucial for ensuring the reliable operation and performance of the uninterruptible power supply. Factors to consider when selecting direct current link capacitors include voltage rating. The capacitors must have a voltage rating that is higher than the maximum direct current link voltage to prevent breakdown. Capacitance value is also something to think about. The capacitance value must be sufficient to provide adequate energy storage and filtering. Equivalent series resistance should be thought about too. Low equivalent series resistance is important for minimizing losses and ensuring efficient operation. Ripple current rating is another component, and the capacitors must be able to withstand the ripple current generated by the inverter. Lifetime is important, and the capacitors should have a long lifetime to minimize the need for replacement. Temperature rating also needs to be taken into account, and the capacitors must be able to operate reliably at the operating temperature of the uninterruptible power supply. The type of capacitor used for the direct current link can also affect the performance of the uninterruptible power supply. Electrolytic capacitors are commonly used due to their high capacitance and low cost, but they have a limited lifetime and can be sensitive to temperature. Film capacitors offer higher reliability and longer lifetime, but they are more expensive and have lower capacitance. Ceramic capacitors have very low equivalent series resistance and can operate at high frequencies, but they have limited capacitance and can be sensitive to voltage. The direct current link voltage is also affected by the load connected to the uninterruptible power supply. As the load increases, the direct current link voltage will tend to decrease. This is because the inverter is drawing more current from the direct current link capacitors. To compensate for this voltage drop, the uninterruptible power supply control system will typically increase the duty cycle of the inverter switches. However, there is a limit to how much the duty cycle can be increased. If the load is too high, the direct current link voltage may drop below the minimum allowable level, causing the uninterruptible power supply to shut down. Therefore, it is important to ensure that the load connected to the uninterruptible power supply does not exceed its rated capacity. In addition to the load, the direct current link voltage can also be affected by the input voltage. If the input voltage is too low, the direct current link voltage will also be low. This can cause problems with the operation of the inverter and may even prevent the uninterruptible power supply from starting up. To prevent this, most uninterruptible power supplies have an automatic voltage regulation circuit that boosts the input voltage if it is too low. The automatic voltage regulation circuit typically uses a boost converter to increase the voltage. The boost converter is a switching power supply that uses an inductor and a switch to increase the voltage. When the switch is turned on, the inductor stores energy. When the switch is turned off, the energy stored in the inductor is transferred to the output capacitor, increasing the voltage. The automatic voltage regulation circuit is typically controlled by a feedback loop that monitors the direct current link voltage. If the direct current link voltage is too low, the feedback loop will increase the duty cycle of the boost converter, increasing the input voltage. Conversely, if the direct current link voltage is too high, the feedback loop will decrease the duty cycle of the boost converter, decreasing the input voltage. The automatic voltage regulation circuit is an important feature of uninterruptible power supplies that helps to ensure stable and reliable operation, even when the input voltage is fluctuating. In summary, the direct current link voltage in an online double conversion uninterruptible power supply is a critical parameter that affects its performance and reliability. The appropriate direct current link voltage depends on the uninterruptible power supply topology, the input voltage, the output voltage, the load, and the component ratings. Proper selection and maintenance of the direct current link capacitors are also essential for ensuring stable and reliable operation.